By the date of its perihelion, 3I/Atlas had already begun to intrigue astronomers with behavior that was far from ordinary, and the first clear sign of this came in the form of a measured non-gravitational acceleration acting on the object. This acceleration was carefully reported by Davide Farnokia, a navigation engineer at NASA's Jet Propulsion Laboratory in Pasadena, whose expertise in celestial mechanics and orbit determination made him the ideal person to investigate such an anomaly. His report drew attention because objects passing through the solar system, particularly interstellar visitors like 3I/Atlas, are typically governed almost entirely by gravitational forces. When something deviates measurably from a purely gravitational trajectory, it demands an explanation, and that explanation often turns out to reveal unexpected things about the object's physical nature. Farnokia's analysis established that at a perihelion distance of 1.36 astronomical units, about 203 million kilometers from the Sun, 3I/Atlas experienced a non-gravitational acceleration with two distinct components within its orbital plane. One was a radial acceleration directed away from the Sun, measured as the equivalent of 135 kilometers per day squared, corresponding to roughly 9 millionths of an astronomical unit per day squared. The second was a transverse acceleration of about 60 kilometers per day squared, or approximately 4 millionths of an astronomical unit per day squared. Both of these values were small but significant, and their presence raised the central question: what was causing the object to accelerate in a way that gravity alone could not explain? The most natural interpretation would be that 3I/Atlas was undergoing outgassing. The ejection of gas produced as volatile ices on its surface were heated by sunlight and sublimated into space. In the case of comets, this process acts much like a series of tiny thrusters, producing a reactive force that pushes the body in the opposite direction of the expelled material. If 3I/Atlas were behaving like a comet, then momentum conservation demands that a measurable acceleration would correspond to a measurable rate of mass loss. In fact, the mass loss required to generate such an acceleration would be large. With typical thermal ejection velocities of a few hundred meters per second, one can estimate that the characteristic timescale for the object to lose half its mass would be around 6 months. That means that during the roughly 1-month interval, in which 3I/Atlas travels across a spatial scale comparable to its perihelion distance from the Sun, it would lose on the order of 10% of its total mass. Such a dramatic loss of material would create a conspicuous plume surrounding the object, an extended atmosphere or coma rich in gas and perhaps dust, so large that it should be observable with modern instruments, even from great distances. For this reason, the coming months, particularly November and December of 2025, were predicted to be scientifically important. ESA's JUICE spacecraft would be in a position to detect the earliest signs of this outgassing in the first week of November. Later, on December 19, 2025, when 3I/Atlas makes its closest approach to Earth at a distance of roughly 269 million kilometers, many of the world's most powerful telescopes, including Hubble and the James Webb Space Telescope, will have an opportunity to observe it with exceptional clarity. These observations should reveal once and for all whether the object has indeed undergone the massive evaporation that would be required to explain the non-gravitational forces measured at perihelion. Adding to the mystery is the remarkable brightening of 3I/Atlas observed by multiple spacecraft instruments, including STEREO, SOHO, and GOES-19, during September and October of 2025. A recent study analyzing this data showed that the object's brightness rose sharply, following a steep dependence on its distance from the Sun proportional to r, with uncertainty of about 1. This is much steeper than what is typically seen in natural comets, which brighten due to the reflection of sunlight by dust and gas released from their surfaces. Such an extreme dependence suggests an energy release far more intense, or more concentrated, than standard cometary sublimation. While evaporation of volatile ices could still account for such behavior, the magnitude of the brightening raises legitimate questions about whether outgassing alone is sufficient or whether some additional mechanism might be contributing. Brightness anomalies in interstellar objects are particularly noteworthy because they cannot be easily explained using models developed for solar system comets, whose compositions and histories are better understood. Another layer of complexity comes from the unusual color of 3I/Atlas. Reports indicate that at perihelion, the object appeared significantly bluer than the Sun, which is unexpected for any natural comet. Dust, especially fine dust typical of cometary tails, usually reddens scattered sunlight because it preferentially reflects longer wavelengths. Additionally, because 3I/Atlas is estimated to have a surface temperature around 20 times cooler than the Sun's photosphere, one would expect it to scatter light in a manner that results in a color even redder than the Sun's, not bluer. The fact that the object instead exhibits a blue hue forms what has now become the ninth major anomaly in its observed behavior. Some have speculated that such a blue appearance might indicate the presence of ionized carbon monoxide, which can emit strongly in the blue portion of the spectrum when exposed to intense solar radiation. This would still allow for a natural explanation, though it would require unusual environmental or compositional conditions. Others have suggested a more exotic possibility, that the color might originate from an internal heat source, such as an engine or another form of artificial illumination. While this interpretation remains greatly speculative, the clustering of anomalous properties, non-gravitational acceleration, extreme brightening, unusual spectral color, and several others previously documented, does prompt some observers to consider technological explanations alongside natural ones, especially given that 3I/Atlas is only the third confirmed object known to have entered our solar system from interstellar space. Despite the reported non-gravitational acceleration, calculations show that the total displacement of 3I/Atlas from its expected gravitational trajectory would be modest, on the order of 10 Earth radii over the course of a month. This deviation, while scientifically significant, is nowhere near large enough to alter the object's path in a way that would bring it into close proximity with any planet. In other words, even with the anomalous force acting on it, 3I/Atlas poses no threat and will continue along a path largely consistent with predictions, albeit with noticeable but small deviations that help astronomers measure its behavior with greater precision. The discussion of anomalies naturally brings to mind a moment from a different event that took place on the same day. At Harvard's Institute for Theory and Computation, where weekly Thursday luncheons gather more than 100 astrophysicists to share recent research, one of the presentations focused on another major puzzle in modern astrophysics: the discrepancy between the observed expansion rate of the universe today and the rate predicted from observations of the cosmic microwave background, the thermal radiation leftover from the first few 100,000 years after the Big Bang. The presenter demonstrated convincingly that this discrepancy persists beyond the limits of statistical uncertainty, and yet the theoretical community has struggled to produce a model that explains it elegantly. Following the talk, I felt it important to remind the younger theorists present that it is poor scientific practice to dismiss observational data simply because it does not fit neatly into existing theoretical frameworks. Data should guide theory, not the other way around. This philosophy applies equally well to cosmological anomalies and to the puzzling behavior of interstellar objects like 3I/Atlas. Science advances when observations reveal something unexpected, forcing us to confront the limits of our understanding. In the case of 3I/Atlas, the collection of unusual features, non-gravitational acceleration, steep brightening behavior, unexpected color, and the potential for extreme mass loss, demands careful study rather than premature dismissal. Whether the explanation ultimately turns out to be fully natural, involving uncommon combinations of volatile chemistry and interstellar weathering, or whether it points toward mechanisms that challenge our assumptions about interstellar objects, the correct response is to follow the data wherever it leads. The coming months of observations, particularly those made during the object's close approach in December 2025, will provide crucial clues. Whatever the outcome, 3I/Atlas offers a rare and valuable opportunity to deepen our understanding of the diverse bodies that populate our galaxy and occasionally pass through our cosmic neighborhood.